Okay. Good day, everyone, and welcome to our technology session. I'm Ilana Koegelenberg, the Market Intelligence Manager and co-founder of Atmosphere, and I'll be moderating this session. I'm joined by Armin Hafner today, who has very impressive titles, Professor Doctor of Engineering and Refrigeration Technology at the Norwegian University of Science and Technology at NTNU. And yeah, he's also the president of Norwegian Society of Refrigeration. And during the past decades, his research and development has been focusing on refrigeration and heat pump technologies with natural refrigerant, natural working fluids. So Armin should be no stranger to many of you. He's been part of the natural refrigerant family for a long time and done some very impressive things. So today, Armin will be sharing the latest information on technology trends with us. And as someone who's worked in the industry for so long and has such an impressive technical knowledge on the subject, I would say he's definitely the right person for the job. But before I hand over to Armin, just a reminder, there's a live discussion button you'll see at the bottom of your screen. So please remember to post some questions and polls and discussions throughout. We'll take the questions at the end. For now, over to you, Armin. Welcome.
Thank you, Ilana, and very welcome from Norway. Thanks for having me this morning to present you some technology trends which I collected during the past and would like to bring over to you. And I start with a short introduction why we are doing this and give you then some examples on natural working fluids, how they can be smart applied. And I will focus today mostly on hydrocarbons and CO2. And I give you a short summary and a conclusion. So, state of the art so far in many places on this globe, also still in Europe, F-gases have been used and are still being used. What do we see there is, we see that we had a depletion in the ozone layer. We're not finished with that. Around the globe, there are still releases of these kind of fluids. We have global warming due to these fluids, and this has been monitored since Molina and his friend discovered this in the early 70s. So now we see also acidification of our drinking water based on HFCs and the unsaturated HFCs. It's also poisonous decomposition products with the PFAS. So the question is really, do we need these forever chemicals in our society and in our environment, in our drinking water, in our body? Or do we have other sustainable working fluids? And that's the mantra of today, to tell and show you again, to give you more arguments that we can do all our refrigeration efforts with the natural five, I would say. We have carbon dioxide, we have ammonia, we have hydrocarbons, we have water and air, maybe some others also, but these are the main ones. And as you know, with carbon dioxide, you can do hot water heat pumps, more than 5 million of those in Japan. Nowadays, the new electric cars, they have a heat pump system with CO2. Commercial refrigeration has been there for decades. We have low temperature industrial refrigeration with CO2, which is brilliant, down to -53, lately introduced in CERN. We have also heat pump chillers. I will show you some example. Ammonia, great refrigerant for more than 140 years, still going strong in industrial refrigeration, coming in more and more because of charge reduction and the great properties of this fluid. Hydrocarbons are also broadly introduced, more and more residential split units in Asia, light commercial all over the shops in Europe and else. Transport refrigeration picks up it, and we have some mobile air conditioning systems also. And of course, all the home appliances. Water has still some niche products and air also in public transport and so on. So, but let's focus on the systems we would like to talk today. For example, R290, propane and butane, hydrocarbons are very much available across Europe nowadays. Here are some nice examples collected of some colleagues. And we see we can do this even indoor as an installation, even depending on the charge. I will come back on that. We can do chilling, heating, domestic hot water actually. And of course, this system needs integrated safety concepts, but that is now for every refrigerant in the future. except CO2. They all become flammable. So that this is not kind of new or only for the hydrocarbon system. A special requirement and the explosion protection measures must be done. But there has been a lot of effort to develop the standards to make this system safe if they are kind of built according to these standards. And we have then these charge levels depending on where you place this system. And then you can also have individual systems, but then this number is more or less related to the charge of the individual systems, but there are no restrictions to have different of those or several of those in the same place, and follow the standards, and they are not too complicated, and it's very safe to utilize these systems and to convince the end user that this is a good option. So we see also large industrial systems on top of shopping malls or production facilities. Up to several megawatt of cooling capacity is possible with a relatively low charge, as you can see these systems. And this is good news. I mean, there are alternatives to HFC chillers, and these are products competing in the market and already gaining more and more market share, which is a good news for our society. We see also propane, butane high temperature heat pumps. This is on the left side, you see an installation introduced in Norway in a dairy where they utilize this two-stage system with the propane in the bottom, producing chilled water with an evaporating temperature of -5. The propane system rejects heat at around 50 degrees, where the butane system picks up the heat and delivers it at 120 degrees C. So this is a relatively high temperature lift, the source at -5, while the distribution or the hot water which is produced is at up to 120 degrees. Here on the right-hand side, I show you a field test or field result. The input power was about 153 kilowatt. The exit hot water capacity was 330 kilowatt, lifting the water from 96 to 106 in this case, while the chilled water came back to the system with 4 degrees and was supplied by 0.5 degrees, representing 152 kilowatt for this one single unit. And this dairy is very happy with this kind of system. So after this field trial, they will install more of them. And this is part of an investigation together with SINTEF, and they have a project here in Norway where they support this kind of innovative heat pumps for high temperature heat pumps. We also see that in CO2 systems, the big brothers have arrived. Big brother means the biggest compressor now from Bitzer and Doreen are up in the range of around 100 cubic meter an hour. This is really what the market has been looking for a long time. Now it is possible to build systems up to above the megawatt size with a decent number of compressors. This is what industrial refrigeration needs. This is very good news and thanks to Bitzer and Doreen and the others, providing more and more a wider range of compressors, high efficient compressor, which enables CO2 to enter even more markets. We see also a trend to utilize CO2 in heat pump systems. This is an example of Finangi from Denmark. They produce these kind of racks now for district heating, where air is the heat source for the district heating, supplying 75-degree water into the system, while the return is good in Denmark. It's down to 40 degrees, and it can work in all air temperatures, which are typical for the Scandinavian, North European area, from 20 plus to -20. And their systems are able to provide up to 1.8 megawatt per skid. That is very interesting for Denmark, phasing out fossil fuel, and they want to be on the green agenda very soon. And these kind of heat pumps will be more and more installed to supply heat into existing district heating systems. And these units can be switched on short notice. That's a very good point. So we are seeing that this is a trend to be continued also by others. And these are, in that respect, actually small systems. I know there are systems planned up to 50 megawatt with CO2 as a refrigerant, utilizing heat from the seawater heat, which is then heat pumped into the district heating systems. Similar concept like this. We see also that we can have a CO2 heat pump chillers where we utilize both the cold and hot side, similar to what I showed you previously with the propane butane heat pump. Utilizing both sides, that's a clue for to get the energy efficiency and implement storage where it is necessary. But this heat pump chiller developed by NX shows that it is possible to really outperform even existing HFC chillers, and we can provide a future-proof solution which is not non-flammable, especially in the environment around hotels inside the city center, where it might sometimes be challenging to have a flammable refrigerant. Even we can build very efficient chillers with propane, providing all the safety measurements, but sometimes this might be a very good option, especially when you need very hot water. These systems can produce temperatures up to 90 degrees, or lift the water temperature from 10 degrees to 90 degrees in one unit, which then reduces the number of storage devices you need for hotels and so on. It's a very good product, and this will enter more and more marketplace. What is very unique, you have when you introduce the ejector is a small pumping device operated by the expansion work, and in this case it is utilized to kind of create two temperature levels, elevate the suction of the compressor, improve the energy efficiency. So it means you can deliver 7-degree water in this case and kind of evaporate at even higher temperature, because the ejector is doing the booster is the kind of the booster in this system to bring up the level for the suction for the compressor, which improve the energy efficiency a lot. So that's a very smart implementation or utilization of the ejector for these kind of systems. When it comes to supermarkets, please follow the market trends shown by Ilana later on. She shows you the latest results on how many transcritical systems are around the world. I'm pretty sure there are many more than this figure from last year, because if you look at the production of all these components, there must be more. And of course, we have some challenges with some of the production and the distributions today, but I think this will recover soon, and we can continue the growth of replacing HFC systems with CO2 systems, which are energy efficient all over the globe if the engineers and the designers do a good job. So it is possible to do that, and the customers, the end users, have not met one of them who regret that they have switched to CO2. So this trend will also follow up, and it will continue all over the world. When it comes to booster systems and ejectors, we have seen a lot of interesting innovations the last year, and now it's a little bit go back to the simpler systems to make this a kind of a global application. And on the right-hand side, you see a simple booster system. It has an ejector there, but what we want to show is that it is possible to replace the high pressure control valve with the ejector, and then actually having, having a ejector system which can utilize this nice advantage of utilizing the expansion work all a year. And in case of utilizing such a multi-ejector, it has so many functions inside, which I would like to show you, which enable to do this. So if we use the ejector in a traditional way, you see that we have a high pressure coming in. So we have the medium temperature compressors here. You have the gas cooler rejecting the heat. We have an internal heat exchanger which provides some superheat. Then the high pressure comes in here, and it is distributed to the port, high pressure port in the ejector, which is the upper connection. On the middle connection, we have the suction port, which comes from the empty evaporators, all the chilled good is connected to this suction port. So when the ejector is operating, it is expanding through the nozzle, sucking what comes from the medium temperature medium temperature evaporators, and distributes the two-phase back into the liquid receiver at the elevated pressure. So that is the pressure level the compressor sees, while normally, traditionally, the compressor would control the pressure level in the empty evaporators, but in this case, it's just controlling the pressure in the liquid receiver, low pressure receiver, which is slightly higher. As long as the ejector can bring all the vapor from the empty evaporators back into the receiver, everything is fine. At lower ambient temperatures, the ability to pump is going down, and in this case, the ejector is not utilized. We are just closing the port here, and it is just the high side pressure is not distributed anymore through the ejector. It's distributed at the lower pressure level to all the small expansion devices in front of every evaporator. By doing so, we still maintain the flow back to the ejector, but now the flow goes through the ejector passively and just back into the receiver. We have measured these pressure drops and the system. I will show you in a minute. So that means we have a very simple system, just switching between ejector mode, passive and active mode, and nothing else. And by doing this, we can have a high efficiency on the evaporators and the simplified system. It has been measured that we can outperform any other system. We see the basic standard booster system is in the bottom. When we do parallel compression, we get an improvement. The higher the amount of flash gases we can remove. But you see, with this ejector system, we can really outperform and help to boost the seasonal efficiency in the warm climate. Here is the gas cool outlet temperature. Here we see the annual energy efficiency ratio, meaning with this kind of simple system, which is a traditional booster system, a little bit reconfigured to be a low pressure system, low pressure receiver system, it is really possible to really boost the energy efficiency and keep the system rather simple. That is very important nowadays. We have tested this in our facility where we have a real shop, supermarket system with a lot of different flexibility and possibility to test this. So these are measured values with the same system configurations for different kind of systems and load conditions. So that's why we know that this will work also in the field. So next time we will build this kind of system in a project, we will implement this concept together with the partners. This brings me already to a summary in a way to show you on the left-hand side the different applications, and on the upper kind of the columns indicate which kind of working fluid do we have a solution for the different application. In domestic applications, we see that we have CO2 for hot water heat pumps, we have hydrocarbon for all these appliances we have around us, even split units. We have in the commercial refrigeration, you can see, of course, we have thousands or 10,000s of transcritical systems and others. There are some ammonia systems around, and of course, a lot of hydrocarbon systems applied in commercial refrigeration. When it comes to industrial refrigeration, heat pump, all except maybe there is no air heat pump system in that respect, but I would say we have a large industrial CO2, ammonia, hydrocarbon, and even water systems which are applicable. And water and space heating heat pumps are also possible with CO2, low charge ammonia, and hydrocarbons, of course. Chillers, similar as with the industrial refrigeration, we can utilize them. We can build this kind of system with all with natural working fluids. Even car and vehicle air conditioning is done with CO2 nowadays. Hydrocarbons are there, and air in some cases for train and airplanes. However, the conclusion, what is important is that all temperature levels and all applications can be cooled by applying natural refrigerants. There is really no technical barrier to replace this current unused synthetic fluorine. We can do that. And it's more about seeing the possibilities than the ghost when you select the refrigerant. It's important that we inform the end user about these alternatives, because the end user, in 99%, they choose the natural one if they get the possibility. And what is also important, no single refrigerant can cover all applications. That's why I showed you there are the different alternatives, and we as the designers, we know when to apply which one. But we can see that the natural refrigerants, they can cover all applications which are covered by the HFCs today, and even more. We can go lower and higher, because none of the fluorinated hydrocarbons can go as low in temperature as we can do with the hydrocarbons, and as high as we can do also with the hydrocarbons. These HFCs, they cover mainly the most profitable market currently in the middle temperature range. When it comes to this forever chemical pollution we are introducing nowadays on Earth, our sector, the refrigeration sector, does have all possibilities to spearhead a complete phase out of HFCs, contributing to this forever chemical accumulation in our biosphere. And we do not compromise safety, food supply, and human comfort. And none job is lost if we do this. It is not a problem on that. There's so much to do and nobody will lose a job. But we have to do this. The green shift is coming, and we are part of the solution when we continue with the natural working fluids. So thanks for listening, and I'm very happy to answer questions.
Thank you so much, Armin. That was very insightful. And it's very good to see that there really is now a solution for every and any application for natural refrigerants. There really is no more excuses. As yes. Armin said, yeah, remember to post your questions in the channel. I have one for you, Armin. Yeah, I think you've listed a lot of exciting technologies. And I was wondering, what are you looking forward to that's coming in the next 5 years on one side, and what do you think is still missing in terms of R&D? Where would be a good place to invest?
You have seen what I told you, the trend now to simplify again. We have had some spearheading, exciting, complicated systems, but the market, we have to bring the technicians, we have to train all the people, and it is to get the wide implementation, we need to simplify the systems, and many of them are already very simple. It's very complicated to follow up, but the training is very important, and the more simple we make these systems, the easier is the implementation, a wide implementation. We have to increase the capacities of this system, and that, as I showed you, going on in all respect when it comes to hydrocarbon compressors, having compressors able to go higher in temperature, having bigger CO2 compressors to really implement this stuff in marine applications. It is really limited, and so on, so on. So, and we see that we will helping also in countries like India and other places to understand how to utilize these kind of natural working fluid for a different application, implementing some demonstration sites, use them for the training, the people need to have hands-on experience, and then it will accelerate. And we'll see this in the next 5 to 10 years, that even in this societies, and it is possible to introduce a lot of these smileys over there as well, actually.
People are running out of excuses for not going natural, I think.
Yeah, I mean,
we're removing those barriers.
I think you have a hard time to explain to a customer why he should not, because the standards are in place. We can build this system. It's very safe. If everybody follows the standard, then there has been a huge job to develop this, to make it really usable. So if people follow this standard, there is no excuse not to do it, because, for example, follow flammabilities and all this. That is also the same issue with this so-called low GWP. They are mainly flammable and they have to follow the same rules. So why should you then introduce such a complicated molecule which is not stable, which will produce all these forever chemicals, which found in mother milk, in small kids, everywhere in the food. So it's really not, there is no excuse anymore.
We've
So
got a...
Yeah, of course, there will be existing systems,
retrofitting
all of them. So there is a market to maintain the current systems. But for new systems, there's one lady in Sweden, she would say, how dare you that you with this stuff? So, and she's right. I mean, we have to maintain what we have built. We have to secure that the end of life is reached in a safe way, but for all the new systems, how dare you?
I've got a few minutes left. I got a quick question. I got a question from Laura Williams about, have you evaluated the total carbon footprint of the systems using natural refrigerants and compared it to systems using fluorinated refrigerants? Clean systems require more components to be used, like ejectors, etc., compared to the technology using fluorinated refrigerants.
Very good question. When we introduce the ejector, for example, we can replace maybe 1 or 2 compressors, because this helps to we can reconfigure the entire pack, and actually we can reduce the number of components if we do it in this way. And at the end of the day, it's the kilo which counts, the kilo of steel, the kilo of copper tubes, and so on. And that has been shown before, that with these kind of systems, even if you go on high pressure components, but the size is much smaller, and the smaller the diameter, the less weight per meter you need at the end. So I'm pretty sure that the total footprint is very good. And what is very important to understand, compared to these low GWP fluids, I mean, this low GWP is a stamp on the bottle. It doesn't account whatever is used on energy and environmental emissions to produce the stuff, get it into the bottle. And this GWP value does also not account for what happens when it is released afterwards. So it's just what's in the bottle. And we should agree on that. This is not the way to look into it. We need to know, as she said, the life cycle analysis, not only on the fluid, yes, and systems as well, but the answer short, no, there's no disadvantage in going into these natural fluids. Also with respect to material use and cost.
Thanks, Armin. Now no one can argue that point anymore.
I think it's not, they have a hard time, I would say, and I can't see it. That's
I think it is the truth. The end users and the customers of tomorrow, like Mark said as well, they're going to be driving it. And like you said, the end user, if you give them the option, that is what they're going to take.
If they know what they buy in the system and take the responsibility for, it's much to have the responsibility for one of these 5 fluids than the cocktail somebody's trying to sell them.
And on that note, thanks, Armin. I think time's caught up with us. Okay. But
thanks for having me, and I wish all of you the best. Stay healthy, and hopefully we can see you soon again in a real event. In case you want to come to Trondheim next year in June, we have the Gustav Lawrence conference. You're all welcome.
Thanks, Armin. So we've got a bit of a 10-minute break right now, so stretch your legs and then check out the networking section.